Diagnostic Nanotools group develops diagnostic technology, as many of you know. You've heard me talking about malaria point-of-care testing many times. Today, I will be talking about the Synthrocyte project, which is an amazing project. I'm sure that most of you have got flu at least once in your life. And I'm sure that all of you know that the influenza virus mutates very fast. And this is what produces these seasonal epidemics. And this is why we need to reformulate the vaccine every single year. What you may not know is that the information needed to produce this vaccine is obtained by a global network of 150 laboratories from all over the world. And they are continuously studying under the supervision of the WHO, which are the viruses that circulate in the planet. And believe me or not, the technique most widely used for this is the hemagglutination assay, the hemagglutination inhibition assay, a classical method that has been a WHO reference since the 1960s, last century. What is the basis of this technique? The basis of this technique is that red blood cells sediment in a microtiter plate, producing these nice pellets, tight pellets. When you add a virus to the equation, the virus binds to the red blood cells, produces agglutination, and you can see in the picture how the pattern is very different. If you add antibodies against the viruses, you will have segrest of these viruses, you will have inhibition of this hemagglutination. This is a very versatile technique. You can use this technique to study how a virus grows in a culture, for example, to produce vaccines or diagnostic kit. And you can use a well-known battery of antibodies to study the viruses in the population to know how it's evolving. You can use a nice battery of viruses to study how the antibodies are in the population, for example, after vaccinating them. Pretty versatile, simple, equipment-free. What's the problem? You need fresh red blood cells obtained from animals. This means that the 150 groups in the network are obtaining red blood cells from different animals on their own. And this impels lots of variability to the method. But how in hell do you change a WHO standard? No one managed to do that since the 1960s. We decided that the only way was to change everything, not to change nothing. What does the virus detect in these red blood cells? It detects the polysaccharides on the surface, specifically sialic acids. This is a type of sugar. What we have been doing over the last years, since the 2018, this hasn't been easy, not as easier as it may look in the pictures. We developed a reagent, a synthetic reagent that is based on particles, a specific type of microparticles that settle down imitating red blood cells. We coat these particles with receptors, and this gives this reagent this binding ability and these surface properties to produce this differential sedimentation. And then because we have this synthetic reagent, we can produce synthrocytes with reagents to imitate avian red blood cells, to imitate mammalian red blood cells, or to make a combination of both of them. This is how the reagent works. We have patented the technology, and you will see how it settles down alone on the left and how it settles down in the presence of an agglutinating agent. And you can see how the sedimentation is very different in both cases. And it's pretty fast, faster than with red blood cells. And here I'm showing you an image of how the synthrocytes settle down in the presence of decreasing concentrations of the virus. We perform a dilution series of the virus, and you have on top the synthrocytes and then red blood cells from 3 different animals. On the right, negative controls, a very nice pellets in all the cases. And as you go left, you have more viruses, and you see this change in sedimentation that is pretty similar in synthrocytes and in red blood cells. We have been doing some testing with viruses obtained from patients. These viruses have to be grown first in eggs or in culture, in cell culture. You cannot detect them directly. And if you compare the results obtained with red blood cells and with synthrocytes, we can detect most of the viruses at least as well or better than with red blood cells. And we also managed to detect antibodies in patients after vaccination with the vaccine. We are less sensitive than red blood cells in this case. We have more interferences, but we managed to detect the antibodies in patients. We are talking about a synthetic reagent, so we managed to do something with the reagent you would be unable to do with red blood cells. We can lyophilize synthrocytes. And in this case, we have flasks of ready-to-use reagent that has only to be resuspended with PBS and used directly. Compared to red blood cells, we have to be obtained from animals regularly, have to be washed several times, have to be titrated every day to normalize the concentration because they start dying when you obtain them. This is terribly simple. What is the conclusion? That we have developed a reagent that seems to be animal-free, it's more reproducible, it's more stable, it's tunable, it's ready to use. It seems much better than red blood cells. Ready to transfer? Not yet. It's too expensive. So this year we are working to decrease the production cost to be able to transfer this to the market and to be used by the whole. This project has got continuous funding from 2018. We have been working for 6 years now, and we have got many, many people involved. Most of the team members have passed by this project. We have also the microbiology department involved. We have 2 of the centers of the national network, influenza network, the one in Valladolid and the CDC in Atlanta. And we have also a company involved, Biosystems, which is helping us to produce the scaling up of this reagent. Thank you.